Hey everyone, and welcome back to the Deep Dive. Today we're looking at an energy source that, well, it holds some fascinating potential, something you might not hear about quite as much when nuclear power comes up. We're diving into the thorium fuel cycle.
And just to set the stage clearly for this exploration, all the information we're digging into today, it comes directly from source material provided by Thorium Energy Ventures.
Ah, okay. So we're really getting their perspective, looking through their lens at this tech. What's their specific focus based on the material they shared?
Right. Well, the material makes it really clear. Thorium Energy Ventures is zeroing in on designing Generation 4 thorium-based small modular reactors, SMRs. And crucially, their approach, the one they're developing, uses a gas-cooled design. And it employs thorium-232 pellets as the actual fuel. That's their specific angle.
Got it. Gas-cooled. TH-232 pellets. Okay. So our mission for this deep dive then, using this info from Thorium Energy Ventures, is to understand, first, what the thorium fuel cycle actually is, and then, explore why this source presents it as such a compelling alternative to, the standard uranium cycle we usually hear about.
Exactly. It's fundamentally a different pathway to nuclear energy, and the material lays out the mechanics and the potential upsides pretty clearly.
Okay, let's unpack that first bit then. What is the thorium fuel cycle? Where does it all begin?
It starts with thorium-232, Theris-232. Now, the key thing here, unlike, say, uranium-235 or plutonium-239, which are, fissile straight out of the gate in conventional reactors, the H-232 isn't. The material calls it fertile.
Fertile, meaning it can become fissile, you can turn it into fuel.
Precisely. Yeah, the whole thorium cycle is built on this idea of transmutation. You start with that TH-232, you hit it with neutrons, and it goes through a couple of steps to become something that can sustain that chain reaction.
Okay, walk us through that. Step by step, how does the material explain that change?
All right, so first step. The TH-232 nucleus needs to absorb a neutron. When it does that, it becomes thorium-233, H-233. And this new isotope, it's unstable.
Right, unstable, so it decays quickly.
Pretty quickly, yeah. The 233 has a half-life of only about 22 minutes. It undergoes what's called beta decay.
Beta decay. Okay, and what's the result of that decay?
That transforms the TH-233 into protactinium-233, Pe-233. Now, Pe-233 is also unstable, but it hangs around a bit longer. Its half-life is about 27 days. This intermediate isotope, Pe-233, is actually quite important in the whole process.
Okay, so TH-232 grabs a neutron because TH-233 decays fast to Pe-233, which lasts for about a month. What's the final step? How do we get the usable fuel?
The Pe-233 undergoes a second beta decay, and it's this decay that finally produces uranium-233, U-233. And according to the source material, U-233 is fissile. So just like U-235 or P-239, it can absorb a neutron, split, release energy, and crucially release more neutrons to keep the whole thing going. Ah, okay. So you start with fertile TH-232, zap it with a neutron, it goes through TH-233, then Pe-233, and you end up with fissile U-233, which drives the power generation. And the material says this whole transformation usually happens right inside the reactor.
Yes, exactly. The source describes this happening within advanced reactor designs. Now, the material does mention examples like molten salt reactors, MSRs, or liquid fluoride thorium reactors, LFTRs, as places where this cycle could happen, where TH-232 might be mixed with a neutron source. But, and this is important, we need to circle back to Thorium Energy Ventures' specific focus.
Right, which you said is their gas-cooled SMR design using those thorium-232 pellets.
That's the one. So, while the basic thorium cycle physics can apply in different reactor types, the perspective in this material, the advantages they're highlighting, are really framed by the potential they see in their particular gas-cooled, pellet-fueled approach. That's why they see the thorium cycle as so promising. Okay, perfect. Let's get into those advantages then. This sounds like where the real pitch for thorium comes into play in this material. What are the key benefits they lay out compared to, say, traditional uranium reactors?
They list several pretty compelling points. Let's start with enhanced safety. The material suggests thorium reactors can offer inherent safety advantages over typical pressurized water reactors, PWRs.
How's that? What makes them potentially safer, according to this source?
Well, they point to features like potentially operating at lower pressures. That right there can reduce certain accident risks compared to the really high pressures inside PWRs. They also emphasize using passive safety systems. These are systems that rely on gravity or natural convection, not active pumps or operator action, to cool things down or shut down the reactor if something goes wrong. The source also links safety to proliferation risk, mentioning the cycle produces fewer problematic isotopes, which they frame as part of the overall lower risk profile. Lower pressure, passive safety, fewer nasty byproducts. Sounds like a safer design philosophy from their viewpoint. And that actually leads right into the next big advantage they talk about, reduced nuclear waste, which, is often the number one concern people raise about nuclear power.
It really is. And the material makes a strong case here. It explicitly states the thorium cycle generates significantly less long-lived radioactive waste compared to the uranium cycle. They explain that, conventional uranium reactors produce these transuranic elements, stuff like plutonium, americium, neptunium, which have incredibly long half-lives. We're talking thousands, even millions of years. That's the stuff requiring that super long-term geological disposal.
Right. And the thorium waste, how does it compare in the material?
The waste from a thorium cycle, as they describe it, is mostly fission products. Now, these are still radioactive, definitely, but they generally have much shorter half-lives. Think hundreds of years, not millennia. This, they argue, drastically simplifies the challenge of long-term storage and disposal compared to that really long-lived transuranic waste from the uranium cycle. Hundreds of years versus potentially millions. That is a really stark difference in the long-term burden they're presenting. Okay, advantage 3, proliferation resistance. How does using thorium make it harder for someone to, get material for a nuclear weapon?
Yeah, this is a pretty fascinating point they emphasize. The U-233 fuel that's produced in the thorium cycle, it isn't pure U-233. It's naturally contaminated with another uranium isotope, U-232. And U-232, as it decays, has daughter products that kick out really high-energy gamma radiation.
High-energy gamma rays. That sounds like something you don't want to be near.
Exactly. It's intensely radioactive, making the U-233 mixture extremely difficult and dangerous to handle without very heavy specialized shielding. So this inherent hotness acts as a kind of built-in safeguard against diversion for weapons. The material contrasts this sharply with plutonium-239 from the uranium cycle, which they state is, comparatively, much easier to handle and more suitable for weapons, making it a higher proliferation risk.
So the fuel itself comes with its own sort of radioactive lock and key, according to this source. Interesting. Okay, advantage number 4, efficient fuel utilization. Does this just mean you get more bang for your buck from the fuel?
Basically, yes. That's what the material highlights. They talk about advanced thorium reactors, like the kind Thorium Energy Ventures is working on, being able to achieve what's called near-complete fuel burnup. Think of it like, actually using almost all the energy potential locked inside the fuel. They compare this to conventional uranium reactors, which they say only tap into maybe 1% to 2% of the energy in the natural uranium they start with. Most of it just ends up as waste.
Wow, hang on. 1% to 2% versus near complete. That's an incredible difference in efficiency, isn't it?
It's a massive difference. Achieving that high burnup means you need way less fuel over the reactor's lifetime for the same energy output. And as the material notes, that can also mean lower fuel costs down the line. You're just getting so much more out of the resource you put in.
That efficiency point makes the next advantage seem even more significant. Abundance and availability. Is thorium actually easier to find than uranium?
According to this material, yes, significantly so. They state thorium is about 3 to 4 times more common in the Earth's crust than uranium. They give some global figures, too. Over 6 million tons of known thorium resources, compared to maybe around 1.8 million tons for uranium. And crucially, unlike uranium, where you need that complex, expensive enrichment process to boost the concentration of the fissile U-235, which is only like 0.7% of natural uranium, TH-232 is basically the only naturally occurring isotope. It's usable as is after mining and processing.
So there's more of it, it's more widespread, and you skip that whole enrichment step needed for uranium.
Exactly. The material points out this simplifies the front end of the fuel cycle quite a bit, and it leverages a much more abundant resource. They even mentioned domestic U.S. reserves, like in monazite sands found in places like Idaho and Florida, hinting at the potential for, energy independence.
Okay, so you got more fuel available, it's easier to process initially, and you can use it way more efficiently. The sheer energy potential starts to sound, enormous.
It really does, and the material gives some specific numbers to try and quantify that energy density difference.
Let's hear the numbers then. How much energy can you actually get from a ton of thorium versus a ton of uranium based on what they provide?
Okay, so they state that 1 metric ton of thorium-232, if it's fully utilized in an advanced reactor, like the gas-cooled designs they're focused on, can potentially produce 1 gigawatt-year of thermal energy. Convert that to electricity, say at a typical 33% efficiency, and you're looking at about 3 million megawatt hours of electricity from that single ton. The reason is, like we said, basically all of that thorium can eventually be converted to U-233 and fissioned.
1 gigawatt-year thermal per ton of thorium used fully. Wow.
Oh.
How does that stack up against the standard uranium fuel, U-308 or yellow cake?
Well, the material uses yellow cake, U-308, as a comparison. 1 ton of that contains about 850 kilos of uranium metal. But remember, in conventional reactors, it's mainly the U-235 doing the work, and that's only 0.7% of the natural uranium. So that's roughly 6 kilograms of fissile U-235 in that whole ton of yellow cake. And then, because those conventional reactors only achieve that low 1–2% burnup, that whole ton of U-308 ends up yielding only a tiny fraction of the energy. They put the figure at about 0.01 to 0.02 gigawatt years of thermal energy per ton.
Whoa, hold on. Let me get that straight. You're saying, based on these figures, it's potentially 1 GW a year thermal from a ton of thoriums in an advanced reactor, compared to maybe 0.01 or 0.02 GW thermal from a ton of yellow cake in a current reactor. That difference is almost hard to believe. It's like comparing a candle to a bonfire in terms of energy density.
It really highlights the core point they make about the vastly superior energy yield potentially achievable with thorium in advanced systems. It comes down to using nearly all the fuel versus leaving, 98–99% of the uranium unused in conventional reactors.
Yeah, that really puts the potential scale of this into sharp focus.
Absolutely. It explains why, from their perspective, looking at long-term energy supply and resource use, they see thorium as such a potentially game-changing option.
So pulling it all together, what's the main takeaway here? Based purely on this material from Thorium Energy Ventures, this deep dive suggests the thorium fuel cycle, especially in advanced reactors like their specific gas-cooled SMR concept, paints a picture of potentially safer, far more efficient, and much less wasteful nuclear power. And all using a fuel that's apparently way more abundant, both globally and right here at home.
That's a good summary. To quickly recap the key points from the source, you've got the transmutation from fertile TH232 to fissile U233. This, when used in advanced reactors, leads to the advantages they stress. Potential for enhanced safety, a dramatic reduction in long-lived nuclear waste, inherent resistance to proliferation because of that U-232 contamination, much higher fuel efficiency through near-complete burnup, and finally the sheer abundance and easier initial processing of thorium compared to uranium.
And connecting this back to you, our listener, why should you care about this exploration based on this source material? Well, think about the potential here for a sustainable long-term energy source, one that could tap into readily available domestic resources, offering, as described here, significant potential advantages over current nuclear technology in key areas like safety, waste, and efficiency.
And maybe a final thought to mull over, drawn from the perspective in this material. Thorium Energy Ventures state they're committed to developing and marketing a thorium reactor. If they or others pursuing this path succeed, and given the arguments made here about thorium's abundance and benefits, what could unliking this energy source really mean? What could it mean for, say, energy independence, or maybe accelerating that shift towards cleaner power on a truly large scale? That's the big picture potential this material points towards.
Definitely a lot to think about. Thanks for joining us on this deep dive into the thorium fuel cycle, guided by the source material provided by Thorium Energy Ventures.
And yeah, if this has piqued your interest and you want to learn more directly from them about their specific project and progress, the source material says you can check out their website. It's www.thoriumenergyventures.com, or you can reach out by email to info@thoriumenergyventures.com.
We hope this gave you some valuable insights into this alternative nuclear pathway. Until the next deep dive.